All right, so section 1.4 just deals basically with algebraic principles with regards to matrices. So when it comes to algebra with real numbers, we are quite used to the way that we multiply real numbers, how we add and subtract real numbers, how we multiply real numbers, or rather how we multiply, say, a real number with the sum between two other real numbers. That's also known as the distributive property of real numbers. And a whole lot of other things. How do we invert a real number? What's the inverse of a non-zero real number? So now the thing that we are trying to establish here is we're trying to now do the same for matrices. So how do we compute the inverse of a matrix? How do we define distribution? How do we define associativity? And so on and so forth. Right, so that brings us to inverses, algebraic properties of matrices, and specifically properties of addition and scalar multiplication. So properties of matrix arithmetic. So let A, B, and C be such that the following operations are defined. And let C and D denote scalars. Right, so you'll find that the following properties that you're going to see is very similar to how we conduct multiplication and scalar multiplication and finding the inverse, how we conduct that with real numbers. Okay, so first of all, with matrices, the commutativity law holds with regards to addition. So summing two matrices, A and B, doesn't matter in what order I write A and B, the sum of A and B is the same as the sum of B and A. Okay, so that's also in real numbers, that's the case. Then we've also got the associativity property of matrices with regards to addition. If I have three matrices and I add them together, doesn't matter whether I add B and C first or A and B first and then add it to C, it is the same. Then with regards to matrix multiplication, associativity also holds with regards to multiplication. So if I have three matrices A, B, and C, it doesn't matter, well, if I multiply B first with C and then with A, then that's the same as taking A and B first and then taking the result, multiplying it with C. However, what you need to be very careful with in terms of matrix multiplication is that you will see now that matrix multiplication is not necessarily commutative. Remember, when it comes to matrix addition, we said it's commutative, but when it comes to multiplication, it is not necessarily commutative. So if you multiply matrix A with B, it is not necessarily the same as multiplying B with A. So you have to be very careful when it comes to multiplication. Matrix multiplication is not commutative. Right, so you need to be careful there. You can't switch A's and B's around there. You always have to maintain a stable order when it comes to multiplication with matrices. Okay, and that's a mistake that is quite common, is, students, if they write A, B, and C together, they tend to, play around with the order. They equate those two things, and you've just switched B and C around there, and when it comes to multiplication, one is not allowed to do that. Then the left distributivity law holds for matrices. So if I take a matrix B and I add it to C and I multiply that on the left with a matrix, then that is still the same as multiplying in from the left with A. So I multiply each term in the sum on the left with A and I add the two together. Okay, and again, if we go back to this law here, it is a mistake. It is a mistake to do the following. If you write down A times B plus C, then you will be making a mistake. If you do this, for example, you multiply A with B, and then to that you add C, and then you multiply A with C. It's a mistake. Why? Because you're multiplying here, and then you're multiplying that, and what you're doing is you should keep the order the same. So if you multiply from the left, you should stay on the left. But here I multiplied on the left, which is still correct, but there I'm multiplying on the right, which is incorrect, because C times A is not necessarily the same as A times C. So again, when it comes to multiplication, always be very careful when it comes to matrices. Do not disregard everything you know that you've learned with multiplication on real numbers when it comes to matrices. So the same things don't hold for matrix multiplication, the same things that you're used to. So always remember, when it comes to multiplication, do not switch matrices around unless you know for sure that they are commutative. Okay, but when you're given an arbitrary matrix, there's no way of telling whether two arbitrary matrices are commutative or not. Right, so again, when you have this right distributivity, if you multiply, so what this is if you add a matrix A and B, and you multiply that sum on the right with a matrix C, then you can go and distribute C you can multiply C on the right-hand side with both B and A and add the two together. Note that they start with C on the right-hand side, and then they keep C on the right-hand side. So they're not switching A and C around and B and C around. They multiply on the right, on the left-hand side, and they keep multiplying on the right-hand side. So again, guys, be very careful. When it comes to multiplication in matrices, you are not allowed to switch matrices around the way you used to with real numbers. Okay, here we've got just a continuation. Here we have how it works when it comes to subtraction. If you take a matrix B and from B you subtract C, and you multiply that on the left with the matrix A, then remember you're multiplying on the left-hand side on the left with A. So on the right-hand side, you must also, when you distribute A over the difference between B and C, you need to keep A also on the left-hand side. So again, that's AB minus AC. Then also another variation is if you multiply the difference between B and C on the right-hand side with A on the left-hand side, and that is going to be on the right-hand side BA minus CA. Right, so again, because they started on the left-hand side by multiplying A from the right, so they A is here on the right-hand side, and they're multiplying it in that direction. They stay on the right-hand side here. They stay on the right-hand side with A. Okay. Again, they did not switch A and B around and C and A around. Then we have the next one, which is a scalar multiple distributed over the sum. Now, when you multiply a matrix with a scalar, right, then it doesn't matter whether you multiply a scalar with a matrix from the left or whether you multiply a scalar with a matrix on the right-hand side. Because remember how we defined scalar multiplication of matrices? You took the scalar and you multiply each entry of the matrix with a scalar. And whether you multiply each entry of the entries of a matrix, whether you multiply each entry on the left-hand side or on the right-hand side, it doesn't make a difference. It's still the same thing. All right, so that you can switch around when it comes to scalars. but not when it comes to matrix multiplication. So multiplying a sum between two matrices on the left-hand side with a scalar, you can easily distribute the scalar over the sum. And then also if you have a sum between two scalars and you multiply a matrix with that, then again you can multiply the matrix and distribute it over the sum of the two scalars. And again, as I said, if you multiply a scalar with a matrix A on the left, it's the same as multiplying a scalar of a matrix on the right hand side. So there you can actually switch the two around. You can do that. You can do that as well. Okay, that you can do because that is a scalar and that is a scalar. C and D are not matrices. Okay, so that you can do. Then here, when it comes to multiplication, if you multiply two scalars and you multiply that with a matrix A, then that associativity law holds. You can first multiply the first scalar in your product of scalars with the matrix A, and then that end result you can multiply with C. Okay, so that associativity law holds. And then if you have a scalar and you multiply it with the product between two matrices A and B, then you can also go and play around. The scalar can move at will between the product between two matrices. So although you can't switch A and B around, you can take the scalar K and you can write it, you can first multiply it with A and then multiply that whole Ka matrix with B. Or you can take the scalar K and you can go and write it in between A and B. And then you can group K and B together and multiply that out first and then multiply on the left with A. So what they do there is, remember, the scalars have free will, but the matrices are bound by their order. So you can't switch the order of two matrices. A occurs before B in all these cases, right? So if A occurs first, it comes before B all the time. Okay, so again, always be careful when it comes to matrix multiplication. Don't just assume that you can switch, or don't just assume that matrix multiplication is commutative. It isn't. Matrix addition is commutative, but not matrix multiplication. All right, so here's just an example how we apply those distributive laws. Let's just take two matrices A and B, and let's just solve this equation for x quickly. How does it work? Again, it is not complicated. Let's quickly look at that. Okay, so there we've got the matrix A and B, and we've got the matrix equation to solve. So again, that is going to be not very straightforward to do. So from that, we get that 2 times the matrix A minus B. This is the distributivity law that we're applying, plus 4x. And on the right-hand side, the distributivity law that we're applying again, that's 3x minus scalar multiple times the matrix B. And again, from there, let's just simplify that. So that is then on the left-hand side, we get x. And on the right-hand side, we have minus 2a minus b, minus 3b. And again, we're applying the left distributive scalar law. So that's minus 2a plus 2b minus 3b. And that is going to be minus 2a minus b. Right, so again, just substitute that in. What is minus 2a? That is going to be the matrix. We know how this works. Minus 2, minus 4, minus 6, minus 8. Okay, and what's minus b? That is going to be plus 1, 0, minus 1, minus 1. Okay, and you can quickly do that. So that then becomes the matrix. We know how to add matrices now. It's minus 2 plus 1, which is minus 1. Minus 4 plus 0, which is minus 4. Minus 6 minus 1 is minus 7. And minus 8 minus 1 is minus 9. Okay, so we have solved for x. We have solved for x. We have solved for x as this matrix on the right hand side. Okay. Right, so that was an application of left scalar distribution laws. Okay, so right. Right, this brings me to the important thing I mentioned earlier, which is the non-commutativity of matrix multiplication. So what is commutativity again? When it comes to addition, we say matrices are commutative under addition. So if I've got A and B, A plus B is the same as B plus A. That is commutative. A and B are, well, matrix addition is commutative. A plus B is the same as B plus A. However, matrix multiplication is not necessarily commutative. And here's an example. Matrix multiplication is not commutative. In general, A times B is not necessarily the same as B times A. So if I take my matrix A there and I take my matrix B there, if I multiply that, we know how to multiply now. That is a 2 by 2 matrix, 1 0 3 0. And then if I switch these two matrices around and I have them switched around, there I've got my first one there and there I've got my second one there. If I multiply them out that way, then I get 1 2 0 0. And there's definitely, those two matrices are not the same. Okay, so matrix multiplication is not commutative. That's why I said in the beginning, when you multiply, you have to be very careful. You cannot just assume that A times B is the same as B times A. And here's a perfect example where it's not. So if A times B is equal to B times A for two specific matrices A and B, then we say that A and B are set to commute, right? Commute. So when you have that A times B is the same as B times A, then we say the two matrices are commutative or they commute. Okay, so here is an example. Here they give me an arbitrary 2 by 2 matrices and they ask me to find conditions for A, B, C, and D such that A times B is the same as B times A whenever A is this specific matrix, 1 minus 1 minus 1, 1. Right, so there we've got our two matrices, and what we're going to do is quickly look at, this is an easy problem to solve. If we take A and we multiply it with B, okay, we first multiply B on the right hand side, and that is equal to, okay, dot the first row of A with the first column of B, so that is A minus C. Okay, then dot the first row with the second column of B, so that's B minus D. Then we move on to the second row and we dot the second row with the first column, and that is going to be C minus A. And then the last entry, I'm going to dot the second row with the second column, and that's going to be D minus B. All right, now let's look at B. And we multiply B in this case on the right hand side. We multiply B on the left hand side. Okay, so there we've got A dotting the first row of B with the first column of A, we get A minus B again. Then dotting the first row of B with the second column of A, we get B minus A. And then going to the second row and dotting that with the first column, we get C minus D, and then dotting that with the second column, we get D minus C. Okay, because we want A times B to be equal to B times A, we need those two things to be the same, and that happens if and only if A minus C is equal to A minus B, that's the first thing that needs to hold. B minus D needs to be equal to B minus A. Okay, and then C minus D, or C minus A needs to be equal to C minus D. So that will give me the conditions that need to hold. Okay, and then lastly we have that D minus B needs to be equal to D minus C. Right, okay, so from there, that happens if and only if C is equal to B, A is equal to D, A again in the second one here, A needs to be equal to D, obviously, and B needs to be equal to C from there. Okay. Right, so B needs to look like this. B needs to just look like this. A needs to be equal to D. If we go back there, A needs to be equal to D. Right, so we need that there. And B needs to equal to C. Right, so C needs to be equal to B. Okay, so that is what B needs to look like for A times B to be the same as B times A. So it's clear that you can construct a whole many cases where A times B is not equal to B times A by just choosing B to be any matrix where this is not true, where we don't have those entries equal to one another. Right, again, now dangers of working with the zero matrix. So again, this is now a case where if you have the product of two matrices A and B is the zero matrix. What's the zero matrix? The zero matrix is just a matrix where all the entries of the matrix are the same and it is the number 0. Now, if A times B is the zero matrix, it does not imply that A is equal to 0. So if we go back to real numbers, if you got that the product between two real numbers is 0, right? Then we know that that is going to imply that either x is 0 or y is 0. Okay, remember that. And the reason, again, the reason for that is if neither x is 0 nor y is 0, then we know that any non-zero real number is invertible. So therefore, if x is not 0 and y is not 0, and x times y is 0, then you can multiply on the left with 1 over x, and you can multiply on the right-hand side. You can multiply on the right-hand side with 1 over x, okay, like that, and you will get that y is equal to 0, which is a contradiction. And likewise, you can multiply on the left with 1 over y, and on the right with 1 over y, and you can prove that x is equal to 0, which is also a contradiction. So in the real number case, if the product between two real numbers is 0, then at least one of the real numbers is going to be 0. However, if you work with with matrices, right, then if you have that the product between two matrices is 0, it does not imply that either A is the zero matrix or B is the zero matrix. So do you see now that with matrix multiplication, the things that we used to in real numbers start falling away? And in this case, it isn't true. It's not true that if the product between two matrices is zero, then automatically it means at least one of the matrices needs to be the zero matrix. All right, so that is neither needs to equal the zero matrix. So you could have two non-zero matrices and multiply them together and still get the zero matrix. And here's an example. If you multiply this non-zero matrix with this non-zero matrix, you get the zero matrix. So the implication of this basically is that in matrices, remember in real numbers we had the cancellation law. So we had that if AX is equal to BX, no, we had the cancellation law. If AX is equal to AY and A is non-zero, then you could invert A and multiply that on the left-hand side and do the same on the right-hand side. And from that, then you could cancel and then prove that X is equal to Y. However, with matrices, if a matrix A times B is the same as a matrix A times C, then it does not imply that we can then say that B is equal to C, like we could here. Okay. And the reason for that, the reason why it fails is here we've got a matrix A and we multiply it with a matrix B, and that is equal to multiplying A with a matrix C. And again, here you can compare B and you can compare C there, and you can see that B is definitely not equal to C. Now, why is this the case? Because remember here, if we go back to real numbers, if you have all real numbers are invertible except 0. So you can invert any non-zero real number. However, you cannot invert you can't invert all non-zero 2 by 2 matrices. There are 2 by 2 matrices that you cannot invert. But the question now is, how does inversion in matrices work? What is the inverse of a matrix? And that is what we will get to next. Before we get to inverses, we need to know what an identity matrix is. Now, if you go back to real numbers, right, if x is a real number and it's non-zero, right, then what will be the inverse of x? The inverse of x will be 1 over x, right? And what happens if you multiply an inverse of a real number with the real number? You get 1. Okay, and we say that 1 is the identity number in the case of real numbers. And it's the identity number because multiplying any real number with 1 is the real number itself. So the real number doesn't change if I multiply the real number with 1. Now, you have an analogous concept in matrices. If the question now is, what is the identity matrix in matrices? So the question is, what is the matrix that I can multiply with any matrix A such that the matrix A stays the same, whether I multiply on the left or on the right? Okay, so a square matrix with 1s on the main diagonal and 0s elsewhere is called an identity matrix, and it's denoted either by I or I subscript m by n. So here are examples of identity matrices. You can see they're all square matrices. So if A is an m by n matrix, then obviously I have to multiply on the right by in for it to be valid, because again in is a square identity matrix with n rows and n columns. And when I multiply on the left, obviously my identity matrix needs to have m rows and m columns, because I'm multiplying with an m by n matrix A. So that needs to happen. AIN must be the same as AIN must be the same as IMA, and that must be the same as A. Right. So then we say that this matrix here is called the identity matrix. So let's take a 2 by 3. So in this example here, let's take a 2 by 3 matrix. Right. So what is now in the case of a 2 by 3? What will be how will the identity matrix be defined? It's defined again as these two matrices here. I have to change their rows and columns because I'm multiplying on the left with a 2 by 3 and on the right with a 2 by 3. My multiplication still has to be valid, so I have to adjust the number of columns and rows of I. Right, so there's a 2 by 3, and I need to multiply that with a 3 by 3 square matrix with ones on the diagonal and zeros everywhere else. Okay, so that is going to be a 3 by 3. Multiplying that is still going to be a 2 by 3. So again, that then becomes, so dotting the first row with the first column, we get 1. Dotting the first row with the second column, we get 2. Dotting the first row with the third column, we get 3. And then we move on towards the second row, dotting the second row with the first column, we get 4. Dotting the second row with the second column, we get 5. And then lastly, we get 6. Okay? Right, so basically, again, this matrix here is the same as that matrix there, so it doesn't change under that multiplication. On the other hand, we take the matrix and we multiply on the left-hand side. Again, this is a 2 by 3. Okay, so I need my identity to be 2 by 2. Okay, so that's a 2 by 2 matrix, so that is going to look like that because it's got ones on the diagonal and zeros everywhere else. And again, multiplying that in the same way, we first take the first row and then we go through all the columns. Okay, so dotting that, we get 1. Dotting that, we get 2. Dotting that, we get 3. Okay, moving on. There we go. We're dotting with the first. We get 4. We get 5. And we get 6. Okay, so again, that is how the identity works. And again, we've got this matrix here, the same as that matrix there. So because this is a 2 by 3, if you multiply on the left, your identity is going to look different to when multiplying on the right. But what you need to have is you need to have both. You need to be able to multiply the identity on both sides, on the left-hand side or the right-hand side, and you always need to get the same matrix back. So that's what the definition of an identity matrix is. All right, and it just brings us to this theorem. Just one note: the identity is reduced row echelon form. If R is the reduced row echelon form of a square matrix A, then we have one of two cases. Either A has a row of zeros, right, or the reduced row echelon form is the identity matrix, the square identity matrix. All right, so I mean, this is pretty straightforward. If you look at your the first section 1.1 and 1.2, if you take a square matrix, 3 by 3 matrix, if you take the reduced row echelon form of any square matrix, you're always going to have a situation where you're going to either get at least one zero row at the bottom, or you're going to have a situation where your leading ones, each one of your rows has a leading one. And when each one of your rows has a leading one, and there are n rows, then you're going to have n rows and n columns, each one having a leading one. And if you have an n by n matrix where each row has a leading one, then it's going to be the identity matrix because it's an n by n matrix. All right, so this brings us to the inverse of a matrix. So now we're ready to establish what the inverse of a matrix is. Now, firstly, the inverse is only applicable to square matrices. The inverse of a matrix, or the concept of an inverse, is only applicable to square matrices. So let's look at the definition of an inverse. If A is a square matrix, now remember again, before I go on, how we define the inverse of a real number. If you have a non-zero real number x, then we said the inverse of x is 1 over x. And the inverse of a real number under number multiplication, well, the inverse was defined in terms of multiplication. So what do I have to multiply with x to get the identity number, which is 1? Right? I have to multiply x with 1 over x. So now ask the same question for matrices. If I have a matrix A, what do I have to multiply with A, call it B, so that I get the identity matrix? Okay, but I must be able to multiply A with B and B with A and get the same result. So if A is a square matrix and if B is a matrix of the same size, in other words, it's also square and it's got the same number of rows and columns, then we say if B has the property that if I multiply A with B on the right-hand side, and it's the same as multiplying a B with A on the left-hand side, then if that happens to be the identity matrix in both cases, then we say that A is said to be invertible or a non-singular matrix, and we say B is the inverse of A. If, however, on the other hand, no such B exists, then A is said to be non-invertible or singular. Okay, looking at the examples here. Here we're given a matrix A and we're given a matrix B, and we're asked to show that B is A's inverse. Okay, so what you need to do is we need to look at the matrix A times B, which in this case is 4, 3, 1, 1, and we need to multiply that with 1 minus 3 minus 1, 4. So again, we know how to do multiplication. So we dot the first row of A with the first column of B, and that is 4 plus 3 times minus 1. So that is going to be, that's going to be 1. Then the next one is we dot the, then the next one is we're going to dot the first row with the second column, and we're going to get 4 times minus 3, which is minus 12, plus 3 times 4, which is 12, which is 0. Okay, and then again we're going to take the second row and we're going to dot that with the first column, and that is going to be 1 times 1 minus 1 times 1, which is 0. And then lastly, you're going to dot the second row with the second column, which is minus 3 plus 4, which is 1. Okay, so we get the identity matrix, and that is the identity matrix. Okay, then doing that, we also need to look at b times a. And b times a, you're going to take 1 minus 3 minus 1, 4. You need to check both for it to be an inverse. You can't just check one, you have to check both. Then you're going to multiply that with 4, 3, 1, 1. And again, you're going to get first row with the first column, and you're going to dot that. So that's going to be 4 minus 3, which is 1. Then you're going to dot that again with that, and that's going to be 3 minus 3, which is 0. Then you're going to move on to the second row, and you're going to go to the first column. So that's minus 4 plus 4, which is 0. And then lastly, you're going to dot those two, and that's going to be minus 3 plus 4, which is 1. Okay, and that is the identity matrix. Right, so a times b is equal to b times a is equal to the 2 by 2 identity matrix. So it is clear that b is a's inverse. Okay, next up is another example. Here they ask us, prove that if A is a square matrix with a row of zeros, then A cannot be inverted. Okay, let A be an n by n matrix, and let's say A has a row of zeros. Okay, suppose A is a row of zeros. Okay, so let, for argument's sake, let the ith row of A comprise of zeros only. Okay, so let's assume to the contrary. Let's assume to the contrary that A is invertible. So we know by definition by definition, because A is assumed to be invertible, by definition there exists an n by n matrix B such that if you multiply A with B, that is equal to B times A is equal to the identity matrix, where the identity matrix is a square n by n matrix with ones on the diagonal and zeros everywhere else. Okay, and there's your hypothetical matrix B. It's an n by n matrix, and what we're going to do now is we're going to multiply A with B. Okay, so if we look at A times B and we look at the entry in the ith row in the ith column of A times B, that should be the same as the entry in In, which lies in the ith row and the ith column. Now tell me something, what is the entry of In that lies in the ith row and the ith column? In has ones on the diagonal, right? It's got ones in the diagonal, and that is a diagonal entry. So the entry in the ith row and the ith column of In is definitely, it is 1, okay? Because as I said, In is this matrix here. It's the matrix that's got ones on the diagonal, and it's got zeros everywhere else. Okay, so there is my Okay, there is my identity matrix, and the entry in the ith row and the ith column of that matrix there. If I go and look at the ith row and the ith column there, that's going to be an entry that lies on the diagonal there. So if we take that there, we can say, in addition, what is the entry in the ith row and the ith column of A times B? Well, we know how multiplication is defined. It's defined as the ith row of A, okay, and you're going to dot that with the ith column of B. Okay, so there we've got that. So hence, what is the ith row of A? Okay, we said the ith row of A is a row that comprises only of zeros. Okay, so that's basically going to be a row of zeros. Okay, there's going to be n zeros, and I'm going to dot that with the ith column of B. Alright, there's the ith column of B. Now, if I dot those two vectors, what am I going to get? I'm going to get 0, because I'm going to multiply 0 with that plus 0 times that up until 0 times that. And I'm going to add it all together and get 0. Okay, so that we have there, but what's the problem with that? Problem with that is we calculated that as well. We calculated that whole expression there, and that's obviously equal. So we've got this equality here, equality here, equality there, equality there, equality there. And so what is the problem with that? The problem is that we have a hence 0 is equal to 1, a contradiction. So we have a contradiction. Okay, so whence A cannot be invertible. Okay, so next we've got properties of inverses. So theorem 4 states that if B and C are both inverses of a matrix A, then B must be equal to C. So what that says is the inverse of an invertible matrix. Remember, we say that if a matrix has an inverse, it is invertible. So the inverse of an invertible matrix is unique, meaning that it only has one inverse. So if you calculate an inverse B and in C, and they're both inverses of A, then B has to be equal to C. So you can't get for a matrix two different inverses. And the same for a real number under multiplication. If you invert a real number, there's only one way of doing it, and you get one particular inverse for each real number. Let's look at a 2 by 2 matrix, and let's assume that we're working with an invertible 2 by 2 matrix. And the question is, what is the inverse of a invertible 2 by 2 matrix? Okay, so take a matrix A, 2 by 2, and let's assume that A is invertible. And let's also require that A times D minus B times C is not 0. Question is, what is the inverse of A? Okay, let B be A's inverse. So we want to find this matrix B. So what we're going to do is we're going to look at A times B, and we're going to require that B is A's inverse. So if we multiply A with B, we need to get a 2 by 2 matrix. 0, 1, the identity. And also what we need to do is we also need to require that the reverse is also true. So we need also B to have the property that if I multiply B on the left, I get the same answer. That's the definition of what an inverse is. Okay. So now let's see if we can go and solve for B. So there we've got our two expressions. So solving we get, so we're going to look at 1 first. So from 1, we're going to get 4 equations. Firstly, we're going to take this and we're going to multiply that. We're going to dot that with the first column, and that has to be equal to that entry there. So doing that, we get AX1 plus BX3 is equal to 1. That's the one equation. Then we're going to take the next row and we're going to calculate that and get this entry here. So that is going to be CX1 plus DX3. And that needs to be 0. Okay, that's my one set of equations. Then I need to look at the second column. And we're going to get that entry there. And we're going to take the first row and we're going to dot that and get AX2 plus BX4 is going to be equal to 0. And then lastly, we're going to take the second row and we're going to go and get that entry there. So that's going to be CX2 plus DX4, and that has to be equal to 1. Then getting my second set of equations, take the first row there of the two of number 2. My second matrix equation is going to generate equations. So there we're going to get AX1 plus CX2, and that is going to be equal to that entry there, and that is going to be 1. Then we're going to take the next up, we're going to take the second column, and therefore we're going to get BX1 plus DX2, and we're going to get a 0 there. And then moving on to the second column, or second row I mean, and we're going to multiply that with the first column there, and we're going to get AX3 plus CX4, and that is going to be which entry? It's going to be that entry there, and that's going to be 0. And then lastly, you're going to do that, and you're going to get this entry here, and that is going to be BX3 plus DX4. It's going to be 1.